Hi guys, welcome to this beautiful tropical island. I figure we're going to be talking about sea breezes again, so I thought we would start by showing this. So I know we did a lot of stuff the last lecture. It was pretty intense. We're just going to kind of review it all and kind of summarize it today so that you really get a good idea of what's going on. And it's going to take some thought and some time to do this. So let's jump right in. Before I do though, I do want to make mention that whatever you do on these last three lectures, you need to put it together into a really good set of notes. I really need to show you something. This is going to be kind of cool. There was a student of mine last semester that did a set of notes on things, and I'm going to share it with you in a second here. It's some of the best notes I've ever seen. So if I look at something like this, okay, so let me go here and share my screen, share everything, yay. So this is what her notes look like after some of our lectures. And this was an online version, but just these kind of things. So here, for instance, here's global scales of motion, global scale, synoptic, mesoscale, microscale. The different equations. Now this was a different class, so it's not exactly what we had, but it's similar to it. And here's these kind of diagrams that we were doing. So you get the idea that this is what we're really talking about. When I say I want good notes, this is what it means. Now this person wrote it by hand and did amazing color, but you should be able to put in diagrams. You should be able to type it up. And again, the reason you're doing this is when you take a test, if I said, what are the four scales of motion? You'd go, oh, it's right there. I know where that is exactly in my notes, and you have no worries. Now, for you guys in this class, we're only looking at global, synoptic, or mesoscale. So just so you know. So fantastic notes. I still love to show that. It makes me really happy. Okay, so I'm going to start with this, and I'm going to go to this scenario, which we kind of talked about. And what we're saying is we have this line over here is the ground. It's got the little hatch marks. And that just says we're looking at a cross section. So in this diagram, that way is up, that way is down. So if a person's standing, they're going to be standing on the ground. Now, this blue line is a horizontal surface just higher up. So if you can imagine floating up there, and if you're standing, you're still the head up on top and your feet are on that plane. These black lines are both, as we recall, isobaric surfaces. Surfaces where every place on it is the same pressure. Near the ground, it's 1,000 millibars. Up here, it's 500 millibars. So what I'm saying, and I will again draw the little person here, if I'm standing over here on this part of the plane, okay, then I'm standing where the pressure is less than 500 millibars. If I were standing on this isobaric plane, the pressure is 500 millibars. And air pressure is the weight of the air above me. So higher up, I've got less air above me, so the pressure is less than 500, and I put L, low. And the reason I put the L is because it is lower here than if I were to walk horizontally to this side of the plane, and the pressure would be more than 500 millibars. I have 500 millibars of air above me here. There's 500 millibars. And so I've got this little bit of air between where I'm standing on the blue plane and the isobaric plane. So the pressure over here is high compared to the pressure over here. Okay? So I'm going to go ahead and erase myself. And the idea being is I said, which way does the pressure gradient force point? We've said this many times. The pressure gradient force points from high to low pressure. So it's pointing this way. So which way would the air want to go? Well, it wants to go from high to low pressure, which in this diagram is from the right to the left. Now, air only travels from high to low pressure on the mesoscale, because On the synoptic or global scale, there's the Coriolis force, which changes its direction, okay? So I want you to imagine this is mesoscale. And if it's mesoscale, then the air actually travels from this side, and I'm going ahead and do this. It actually travels from here to here. Now imagine that I'm standing on the ground over here on the left side of this diagram, and I see a bunch of air coming on top of me from over to the right side of the diagram. That means my pressure down here is going to increase. So in other words, the pressure at the ground is higher here because some of the air, watch this is important, some of the air that was over here is now transferred into the column. So at the ground, I have more air above me. If I were to go to this left, the right side of the diagram, what happened to the air? Some of the air that was above me here has left. It's left the column, and so that air pressure becomes lower here. So what does the pressure gradient force do near the ground? Well, the pressure gradient force, let me do this, wants to point from high to low pressure. So it's pointing this way. And it's on the mesoscale, so that means the air is actually traveling from high to low pressure. Mass continuity. Remember what mass continuity is? You have it in your notes. Don't always write everything down a second time, but go to the first time and go, there it is. It says when there's got convergence and divergence, there's got to be vertical motion in between. Well, air is coming together here and spreading apart there. So what's happening is that the air is actually sinking here and rising over there. So I get a circulation that goes this way. Now this is where I don't want you to be confused. This is not air traveling from low pressure to high pressure. Remember, the pressure difference is horizontal. It's a horizontal pressure gradient. In other words, the air pressure here is lower, not than this, but it's lower than that. Over here, this pressure is higher, that pressure is lower. And the air horizontally is moving that way. Now this pressure here is not lower than the air pressure above it. That would be silly. Air pressure is defined as the weight of the air above you. If I go up higher in the atmosphere, the pressure always decreases. This pressure is lower than the pressure over there. So it's always a result of horizontal differences. Now keep in mind that all of this comes about, and I'm going to get rid of those green arrows. All of this comes about because I've got an isobaric surface that is sloped. And what I mean by that is the vertical distance between these two isobaric surfaces is less than the vertical distance between those same two isobaric surfaces on the right side. On the left side, the isobaric surfaces are closer together. That's called thickness, and they're thin. The thickness is little. On the right side, the difference between the two isobaric surfaces, the thickness is greater. So it's thicker on the right side, thinner on the left side. And the reason for that is because the air, let me do this color, the air over here is warm, and the air over here is cold. And we said that's the thickness relationship. That's the thicker, the warmer, over here. The thinner, the colder, over here. So what I have is if I'm going from this side to this side, do you understand that what's changing? Well, I'm going from a column that's colder to a column that's warmer. there is a difference in the average temperature. Okay, so what that tells me is that there is a difference in temperature from here to there, and that tells me that I have a temperature gradient. So if I were to do this, I'd say there, whoops, I don't want that, I want letters. I have a temperature gradient. Okay, so there's a temperature gradient from left to right. I'm changing temperature as I move horizontally. Well, what that causes is the isobaric surface to slope, and therefore horizontally there's also a pressure gradient. So the temperature gradient results in a pressure gradient, and when there's a difference in pressure, what does that result in? That results in wind. So this here, what I'm saying in this scenario is that when I have a temperature gradient, that is going to establish a pressure gradient, which is going to result in wind flowing. Okay? This, my students, my friends, is what we call the thermal wind relationship. Okay, I guess I could make that big because that seems to be kind of important. And that's saying that what causes the wind ultimately is the fact that I have a pressure gradient. But I get pressure gradients because I have temperature gradients. Okay? So, super important. So let's go back and take a look at a couple things here. And what I want to look at is, well, what kind of a scenario is this? Imagine that this is cold because it's over the water. And this is warm because it's over land. Air is traveling from high to low pressure because of the differences in temperature caused by the fact that the sun heats the ground differently than it heats the water. There's differential heating. But it travels from high to low pressure because it's a small scale event, and therefore there's no Coriolis force that matters. So if I go over here, I've got a picture here, and this is exactly what we're looking at. This is high pressure compared to low pressure. Cooler air sinks down, it blows from water to land, the air rises, it should say air rises, not heat. And then you get clouds and precipitation. So what comes with these things? Thunderstorms. So if you look at my little picture here, this is clear sky, but there's definitely breezes. And it probably will have thunderstorms along the coastline. Then the air will come back across over the water and sink. So we get, are you getting the idea that we've got this circulation here? That's a sea breeze circulation. So that's exactly. And why does the sea breeze circulation form? Because the air over the land is heated differentially than air over the water. There's a difference in heating that sets up a temperature gradient, that sets up a pressure gradient, and that makes the air circulate, the winds blow. Now, what makes the pressure gradient, what makes the winds faster in a scenario like this? And the answer is, the greater the temperature gradient, in other words, if I go from the land and it's 80 degrees to the water and it's 70, I'll get a sea breeze. But what if the land is 90 and the water's 70 degrees? I should get a sea breeze, but the winds will blow faster. A greater temperature gradient leads to a greater pressure gradient, which makes the air travel faster. So what determines the speed of the winds? The strength of the pressure gradient, ultimately the temperature gradient, and that's the thermal wind relationship. They're related. All right, now let's go back and let's say instead, let's imagine that this area here is cold because that's the North Pole. Okay? And this area here is warm because that's the equator. Do you agree that the sun is heating the earth differentially because the earth is a sphere? And then we get the same circulation but this is on the large scale. right? We have air wanting to go, so watch this. Air wants to go this way and sink and come back across and go up, and it's transferring the air. That's what it wants to do. But this time, because it's large scale, the air, as it wants to go from right to left, is going to get deflected to its right, which means instead of traveling toward the North Pole aloft, it's going to turn to the right. Okay? So what that's saying is the air up here is flowing, and I can write it here if you understand what I'm saying. It's flowing into the page if it's got the Coriolis force. And that's the way the air is flowing. So it's hard to draw 3 dimensions. I wish I were there, but this is basically into the page. Therefore, the Coriolis force, which is balanced or balancing the pressure gradient force, would be this way. And the air is traveling. So wind's at my back, low pressure's to my left. That's the Buys-Ballot law. And what direction is into the page? The answer is from the, what do you think? From the west. Okay? Because if the air wants to go from south to north, it turns to the right. It's now going to be going to the east. So I want you to imagine this little thing here. I'm going to draw a little box of a map view. I'm going to say that this way is north. I'm going to put a big N there so that you know it's a compass, right? And what we're saying is that the air wants to travel from south to north, equator to pole, but instead it turns to the right, and that is now from the west. It's a westerly wind, and that's where the jet stream is. So on the large scale, the winds don't travel from high to low pressure because of the Coriolis force. So let's review things that we said the other day. I guess I'm going back a lot. What said the other day? We said air wants to travel from high to low pressure. And it does so on the small scale, the mesoscale. But on the large scale, air gets deflected by the Coriolis force to the right, and now the air flows not toward low pressure, but parallel to the isobars. That's geostrophic. So if I were to do this, I'm going to go ahead and draw a circle. I'm going to call those isobars. No, that's not a good one. Let's try it again. Those are isobars, and at the center of this circle is low pressure. What we're saying is that the air wants to travel like the pressure gradient force. It wants to travel, ooh, I'm going to make that smaller. It wants to travel this way, or this way, or this way, or this way. But instead, it gets that on the mesoscale, it would converge. But instead, on the large scale, it gets turned, not as it goes this way, it gets turned to the right. And now the air starts to travel this direction, parallel to the isobars, going around in a circle. And that would be what we meant geostrophic. So it follows the Buys-Ballot law with the wind at your back, low pressures in toward the middle. But why does it eventually, what causes it to eventually flow in toward low pressure? As it sort of spirals in here like this? And the answer is friction. Friction slows the wind down and deflects it somewhat across the isobars toward low pressure. So that what we get is the air spiraling in toward the center where it's converging and going up. Okay? So air always wants to go from high to low pressure, but it doesn't because of the Coriolis force, at least on the large scale, synoptic and global. Eventually, it can work its way there when I've got friction, which brings it in. Now this is exactly what a hurricane does. Air is traveling around the area of low pressure. It's going cyclonically. And I'm going to see if you, I don't know if you can see me, so I'm just going to hide that for a second. It's going around an area of low pressure like this, but it's because of friction, it comes in toward the center, it converges, and then the air rises. Now in a hurricane, the air is going to diverge and it's going to spin this way. So a hurricane is actually spinning kind of like this. So imagine that you take a mayonnaise jar and you hold it in your right hand. Your hand's going to turn counterclockwise, and your top hand turns clockwise. Cyclonic, anticyclonic. So it's like putting the lid on a mayonnaise jar. And when you tighten that lid onto it, if you need to go get a mayonnaise jar or a pickle jar or something, do it. As you tighten the lid, that's how a hurricane structure is. It circulates this way down here, and then it reverses direction and goes the opposite direction. Areas of low pressure in the mid-latitudes where we work is a little bit different. It converges like this, and then it kind of spreads out a different way. We're not going to worry about that for this class. But that's what the thermal wind relationship is all about. Okay, so I'm going to stop sharing just for a second. I'm going to pause. I'll be right back. Okay, continuing. I wanted to open up this document, so I'm going to go back to sharing the screen. And this is our wind systems worksheet. So if we know the definition of wind and what causes it, you should know this. I'm not going to go through everything. How are winds named? The Earth is differentially or unevenly heated because of what? Those are big things you should know. On the global scale, where are there regions of high pressure? Where are there regions of low pressure? Now, this is in the module, but you should go on Google. And on question number 4, I should see an image. You don't have images. That's not good enough. Make this good. What's an isobar? What happens when isobars are close together? Isobars are close together means the winds are going to be fast. Because the closer the isobars are, the stronger the pressure gradient. So that's important. When they're close together, the winds are going to be faster. And basically what that means too is when isobars are close together, we say that they're packed. P-A-C-K-E-D, like you're packing your suitcase. So isobars close together means they're packed and the winds are strong. I'm going to show you something in real time. Yay, let's try this. I'm going to go to models. And this is something that we look at. I'm going to look at the surface isobars. This will have temperatures on there. So these black lines are isobars. And I'm going to look for areas where they're close together. And over here, they're fairly close together. The isobars are packed. And over here, notice they're not exactly parallel because of friction, but where they're close together, the winds are going to be fastest. I want to show you something else. Uh-oh, what's this coming out of the Gulf of Mexico? Lots of isobars together. That's a tropical storm. At the time I made this lecture recording, that's Tropical Storm Cristobal. So this is the forecast. It might even become a hurricane as it comes in there. But in any case, that air is going to be moving fast because the isobars are packed in that region. So I think that's kind of cool. Okay. In addition to the pressure gradient force, what other force affects the direction of the winds? What did you say? You should know 2 of them. We talk about vertical, that's gravity, but that's not the winds, the way we want to define it. 5 facts about the jet stream. That's in your information. Trough and a ridge. Remember, the trough is defined by cyclonic curvature. And you should know this one, the right-hand rule. You should incorporate diagrams in there. The term diurnal talks about day-night. So because a mountain, especially when the aspect is facing south, where the sun's hitting it more directly, you get differences in temperature, ground to the top of the mountain. And during the day, the air wants to go up the mountain where the low pressure and the air is warmer. So lots of little things about that. What 2 things determine the wind speed around the mountain? That's in the module, so I'll let you find that. It explains how downslope winds develop. There's something called a cold air avalanche, which is kind of neat. Hey, draw a description of a sea breeze. You need to put in a good diagram in here. And then what hazard can sea breeze circulations trigger? Well, the answer better be thunderstorms. Okay, so that was a lot of stuff. Let's stop sharing the screen. That was a lot of stuff about pressure gradients. And And I'm not expecting you to do this. If you were in my class, we probably have to go through it a couple of times. But you have a recording of me, and I may be boring, but you can go back and figure that out. If you have questions, you need to email me about what that means, but I'm going to hold you accountable to that, because on the test, not only am I going to give you stuff like we did, and you have to tell me which way the winds would go, what's a trough ridge, that kind of thing. You may not know how it's played out. So you need to know all the rules of how you determine that. So practice that up, do a really good job, and that explains so much of what we need to know about winds. Next time, we're going to be going into temperature and relative humidity, where we start talking about moisture in the atmosphere. And guess where moisture comes from? Comes from over here. Comes from the waters, especially warm waters. The warmer the water, the more that evaporates into the air. So we'll be getting into that next week. Until then, hope you guys have a great day. Bye. Yep. And meeting. We're all